You are not merely floating in space. You are suspended on a membrane of perception. Behind you lies the echo of human history, a chorus of myths, physics, telescopes, and equations. Before you, only a silence that has never been broken. You take a step forward, not with feet, but with thought, into the outermost question. Where does existence stop? And if it doesn't, if it simply stretches forever, what then does that even mean? The concept of the edge of the universe is both ancient and entirely modern. It haunted the imaginations of early mapmakers who inked dragons into the margins of the known world, and still haunts cosmologists armed with supercomputers. But today, the dragons have been replaced by quantum fields, dark energy, and thermodynamic paradoxes. And the boundary, it's no longer a place, but a limit of perception. A moving frontier called the observable universe. Here's the catch. It's not the cosmos that ends, but our ability to see it. The observable universe spans about 46 billion light years in every direction. Not because that's how big the universe is, but because that's how far light has managed to travel since the Big Bang, stretched by the accelerating expansion of space. When you look at a galaxy 10 billion light years away, you're not just seeing distance, you're seeing time itself unspool. You're peering into the past, but this horizon is not static. With every tick of the cosmic clock, the boundary of what we can observe grows by another light day in every direction. Yet the farther we look, the deeper into time we sink. Until we approach a wall, we cannot cross the cosmic event horizon. It is not built of atoms or photons. It is woven of time and motion. Galaxies beyond this horizon are receding faster than the speed of light due to cosmic expansion. Not because they're violating relativity, but because space itself is stretching. Imagine being at sea, on a boat with no oars or engine, watching the shore slowly disappear, not because you are moving, but because the ocean is growing between you and everything else. Eventually, that shore fades from view forever. That is our future, with distant galaxies. The cosmic event horizon defines the farthest edge of our reach. Anything beyond it, stars, galaxies, even entire superclusters, can never influence us, no matter how long we wait. And in a future ruled by accelerating expansion, this horizon will shrink relative to the cosmos. One by one, galaxies will vanish from our view. In 1 trillion years, only the nearest galaxies in our gravitational group may remain visible. The universe will seem lonelier, simpler, and more static, not because it is, but because we'll have lost our window into its depth. This unfolding isolation forces a disturbing question. Will future civilizations know they're alone simply because their telescopes cannot see far enough? Would they assume that the universe is small, static, and finite, because the evidence of its vastness has fled beyond their sky? In that sense, we are living in a cosmological golden hour, perched on a rare moment when we can still see the afterglow of creation and the fingerprints of distant galaxies. But even now, there are shadows on our cosmic map, places where our theories fail to light the way. The theory of cosmic inflation offers one such illumination. In the first split second after the Big Bang, the universe expanded exponentially, faster than light, not as a violation of Einstein's rules, but because those rules apply to matter moving through space, not to space itself. This sudden, incomprehensible expansion smoothed out wrinkles in the early cosmos, stretched microscopic quantum fluctuations into the seeds of galaxies, and gave the cosmos its apparent flatness. Flatness is a strange property. In a curved universe, light would travel in arcs, and triangles wouldn't add up to 180 degrees. But our universe, on the largest scales, seems almost perfectly flat. Cosmic inflation explains why, much like zooming in on a balloon until its curvature disappears, inflation blew up the early universe so massively that any curvature was diluted to invisibility. The implication, what we call the universe. Our observable slice is likely just a bubble in an ocean of space. That ocean, known as the inflationary multiverse, may be birthing new universes constantly. In other inflating regions far beyond our horizon, each bubble could contain different physical laws, different kinds of matter, perhaps even different notions of logic or causality, and we, like fish in a cosmic aquarium, can never peer outside our bubble to see the others. This isn't just poetic speculation. The mathematics of inflation, when taken to their logical conclusion, lead directly to the idea that the universe may be far larger and more diverse than we can observe. And if inflation is eternal, as some models suggest, it may mean that the universe has no global edge at all, just an infinite foam of pocket worlds endlessly inflating. In such a framework, the very notion of a universe is outdated. We would need to redefine existence itself not as a singular event or realm, but as a multiversal process, a field of possibility, blooming without beginning or end. But there's something sobering in this grandeur. If universes are so easily spawned, then what makes ours special? Why does it contain life, consciousness, memory, and dreams? Here, the idea of fine-tuning enters. The constants of our universe: gravity, electromagnetism, the mass of particles are delicately balanced. A slight variation, and atoms wouldn't hold, stars wouldn't ignite, chemistry wouldn't unfold. If there are infinite universes, then perhaps we simply live in the one where life can exist, a cosmic lottery, where winning is rare, but inevitable, given enough tickets. And yet, even if this multiverse is real, we cannot see it. Our observable bubble remains our only lighthouse in a sea of eternal darkness. We search its edges with instruments tuned to the oldest light, the cosmic microwave background, the afterglow of the moment when the universe became transparent. This light, a relic of 380,000 years after the Big Bang, is nearly uniform, yet its faint ripples reveal the fingerprints of quantum randomness writ large by inflation. These ripples seeded galaxies and shaped the cosmic web. They are a bridge between the micro and the macro, between vacuum fluctuations and the grandeur of galactic clusters. But even here, at the limits of what we can observe, strange anomalies whisper, cold spots, asymmetries, potential signatures of a collision with another universe, bruises from a multiversal birth. Diversal. Whether these are artifacts or evidence remains unknown, but they hint that the veil of our cosmos may be thinner than we imagine.
What, then, lies beyond?
Not dragons or angels, but something perhaps more terrifying. The unknown that obeys different rules. A vacuum that births universes. A dimension in which time is not linear, space is not three-dimensional, and identity itself is an illusion. The edge of the universe is not a wall, but a philosophical crisis. It forces us to confront the fragility of knowledge, the arbitrariness of perspective, and the humility demanded by the cosmos. As we drift deeper into this realization, one truth becomes clear. The boundary we speak of is not out there. It is within us, in the limits of our comprehension, our language, our tools. And yet, we press forward, drawing constellations across the abyss. Imagine awakening not to a sunrise, but to a planet unfamiliar in shape and sky, yet still Earth. A world where the continents are strangers, where the wind tastes of minerals never catalogued, and the stars above cast a different constellation across a breathable dusk. This is not science fiction. This is Earth 2 billion years ago. The terrain was silent then, at least to human ears. The forests, deserts, and rivers we know did not yet exist. What lived and moved across the surface bore no resemblance to us. In the shallows of warm oceans, microbial mats breathed out oxygen, slowly reshaping the chemical fate of the planet. This was the time of the Great Oxygenation Event, a planetary metamorphosis that would ultimately make higher life possible. It's here within this alien, ancient Earth that the question sharpens. Could intelligence have sparked, flared, and vanished long before we emerged? At first glance, the answer seems absurd, but only because we look backward through the lens of our own history, as if intelligence is fated to wear a bipedal body, to build cities, to reach for the stars. But perhaps that's an illusion, born of proximity. Evolution does not plan, it meanders, leaps, stumbles. And time is vast enough to allow many different walks of fate. The Saluran Hypothesis, introduced by climatologist Gavin Schmidt and astrobiologist Adam Frank, dares us to consider this. They posed not a claim, but a question. If an advanced industrial civilization had existed in the deep geological past, would we be able to detect it today? Their answer may be, but only barely. Geological time is not generous. The Earth is a master of self-forgetting. Over millions of years, Tectonic plates churn the crust. Over hundreds of millions, entire mountain ranges rise and erode. Over billions, continents shift, oceans vanish, and every surface memory is sanded down to oblivion. The longer back you go, the fewer traces survive. Concrete crumbles within thousands of years. Metal corrodes. Plastics, though durable on human timescales, degrade over millennia. Even nuclear waste decays into geological neutrality in less than 1 million years. If a civilization had risen on Earth 1 billion years ago, its cities would be gone. Its machines would be atoms. Its monuments, if any were built, would have been ground into anonymous sediment. But not everything disappears. Some scars go deep. The Saluran Hypothesis focuses on technosignatures, geochemical footprints left by industrial activity, a sudden spike in carbon dioxide, an anomalous mix of heavy metals, isotopic shifts in marine sediments. All these could betray the presence of large-scale technology, even if we cannot identify the tools. Take our own industrial age. In just 2 centuries, humanity has already left a planetary fingerprint. Fossil fuel combustion has shifted atmospheric carbon ratios. Plastic particles now reside in every ocean. Rare earth metals, once buried deep underground, now lie dispersed across continents. Nuclear detonations have seeded the atmosphere with radionuclides that will persist for tens of thousands of years. From a future geologist's perspective, these could be read as the signal of intelligent life, even if no fossils, no buildings, no machines remained. But here lies the challenge. How do we distinguish natural anomalies from intelligent ones? Nature is a superb engineer. Volcanic eruptions can alter climate. Meteorite impacts can disperse rare elements. Natural nuclear reactors, like those found in Oklo, Gabon, can mimic human designs through pure coincidence. This ambiguity makes deep-time archaeology a game of shadows. Every clue must be balanced against simpler explanations, and yet some anomalies continue to whisper. Consider the Paleocene-Eocene thermal maximum, a dramatic spike in global temperatures about 55 million years ago, linked to a massive release of carbon. The source remains debated. Methane clathrates volcanic activity, or something else entirely. The geological record does not speak plainly. Then there are strange isotopic excursions, abrupt shifts in marine chemistry, and inexplicable concentrations of certain metals in ancient strata. Singularly, they are oddities. Collectively, they are a pattern that dares interpretation. But perhaps the most intriguing idea isn't that we're missing evidence, but that we're missing what evidence should even look like. What if an ancient civilization didn't burn coal, didn't smelt metals, didn't build with stone? What if its technology was biological, its tools engineered from living tissue? What if it communicated not with radio waves, but with biochemical emissions or neural resonance? Would such a society leave behind any trace that modern geology or archaeology could interpret? The answer may well be no. Iyan pa ma'am It's a chilling realization that the vastness of geological time doesn't just erode stone, it erodes intelligibility. After 1 billion years, not only would a city vanish, but the very concept of the city might leave no footprint at all. Yet we continue searching. Why? Because the idea that we are the first and only intelligent beings to evolve on Earth carries an uncomfortable weight. It assumes rarity where time has offered abundance. It assumes a straight line where nature draws spirals. And if we are not alone in Earth's history, if there were others before us, then we must also face the second question. Why did they vanish? Perhaps they self-destructed. Perhaps they transcended matter. Or perhaps they simply passed a threshold. We have yet to approach a technological or ecological bottleneck that defines the lifespan of all complex societies. There's also the unsettling possibility that intelligence isn't favored by evolution, but rather tolerated briefly before its side effects entropy, imbalance, collapse selected out. This invites a haunting reframing. Intelligence may be an anomaly, not a pinnacle, a fleeting combustion in the slow oxygenation of a planet, a pattern that burns brightly and then vanishes, leaving only subtle discolorations in stone. And still, we hope, because hope is itself a form of memory, a reaching back, a reaching forward in a small core drilled from ancient rock. A geologist may one day detect a technosignature, an isotopic quirk, a mineral out of place, a chemical rhythm unlike any seen before. It won't be proof, but it will be a voice, faint and distant, speaking across time. You drift away from Earth, leaving its noise behind, as you float through a cosmic sea emptied of light. In this quiet, you begin to ask, where is everyone? Not just now, but always. The silence between the stars speaks louder than any signal. Imagine ancient civilizations light years away that might have risen and fallen long ago. Their radio beacons, once powerful, now fade into cosmic static. Perhaps they never mastered broadcasting into the void, or their light was extinguished before their reach could cross the gulfs. You wonder, did they even live long enough to build a cosmic signal? This leads to a deeper, unsettling puzzle. The Great Filter. Somewhere in the sequence from inert matter to star-faring intelligence lies a barrier. It may be ahead of us, or behind us. If behind, perhaps thousands of civilizations were extinguished before ever escaping their homeworld. If ahead, we might be flirting ever so dangerously with our own threshold. The silence of the universe could be the echo of filter past or a silent caution of filter future. Next, consider what intelligence might look like elsewhere. Not humans in alien skin, but minds that evolved under extreme conditions on freezing rogue planets, inside crushing gas giants, or far beneath ice-bound oceans. Their intelligence might be post-biological, born not of flesh and blood, but of silicon, quantum fabric, or patterns of pure information. Such beings may communicate not through waves, but through the migration of data hidden in gravitational ripples or the structure of dark matter. And if their form is so radically different, how could we even recognize them? Let your mind drift to stealth civilizations, beings who chose silence, who hid behind the cosmic curtain. Maybe they knew the danger of revealing themselves in a hostile universe. Perhaps they cloaked their megastructures, masked their emissions, even submerged themselves in virtual realities to avoid cosmic predators. What we call silence might be intentional discretion, a strategy for survival. Then there's the alluring but unnerving idea of the simulation hypothesis. Perhaps our universe is an artificial environment, a sandbox in which intelligences far more advanced than us conduct their experiments. If so, the absence of contact isn't cosmic loneliness, it's deliberate design. We could be the data points in a larger study, the chosen subjects of an experiment or an art piece that stretches across dimensions we cannot perceive. It's as though you're an archaeologist of absence, trying to reconstruct civilizations from the gravestones of silence. But here's the paradox. What if intelligence inevitably vanishes? What if complexity itself triggers collapse? Every technological leap brings resource depletion, environmental risk, entropy, leading to implosion before expansion. Intelligent life might be universally self-limiting, a cosmic pattern written into the laws themselves. Or perhaps we're looking in the wrong period. What if cosmic civilizations left their mark millions or billions of years ago, and their signatures have dissipated into background radiation, cosmic dust, or quantum noise? If they existed in the deep past of the cosmos, long before Earth formed, their legacy might be gone or nearly invisible today. Now imagine this. You're not biased by biology. You're a quantum consciousness, evolving inside a black hole's event horizon, or a sentient interstellar cloud of plasma. Your awareness spans centuries in a single thought, yet you leave no footprints, just subtle perturbations in the curvature of space-time. Would we see you? Would we know such existence even counts as life? And yet, the silence could also be a canvas, a space awaiting discovery. Maybe we're just the first to reach out, the first to design probes or unleash gravitational pulses with universal reach. If so, our moment is also an invitation. Should we define cosmic conversation? Should we build not just telescopes, but ethical protocols? Could the ultimate question be, who do we become if we choose to speak across the void? You sense that even the question is a gift. To wonder is to light a spark. To ask is to step beyond Earth's cradle. And perhaps, somewhere in that silence, someone or something is also wondering. Your awareness shifts now to the fabric of space-time, not just the contents of the cosmos, but the currents and textures that shape everything. Imagine drifting through an interstellar river, where gravity's ripples carry the story of every massive object in motion. Black holes, neutron stars, and galaxies all contribute to the tides, sending gravitational waves, faint yet far-reaching murmurs that we are only now learning to detect.
Remember LIGO's first detection in 2016, two black holes, each tens of times the sun's mass, spiraled together and merged. The signal lasted only a fraction of a second. But that brief chirp passed through Earth, carrying encoded tales of the object's mass, spin, and final fate. It was the universe whispering, revealing something deeply fundamental, something previously undetectable by light or telescopes. In a sense, each gravitational wave we detect is like eavesdropping on a cosmic dialogue that spans billions of years. Now, picture the magnetic fields threading through galaxies immense, invisible tentacles shaping gas and dust, guiding star formation, even influencing the path of cosmic rays. These fields are relics of the early universe, evolving over eons. They speak of processes, yet wholly understood, a cosmic memory woven into the darkness itself. Your senses turn inward now, into the bizarre realm of the quantum vacuum, where even empty space teems with fluctuating energy. These ephemeral bubbles of virtual particles are fleeting but fundamental, giving rise to real consequences like the Casimir effect, where two metal plates find themselves mysteriously drawn together by vacuum fluctuations. These currents of the vacuum might hold keys to uniting gravity with the quantum world, a door into realms beyond our current cosmology.
But you don't linger there. The tide drifts you outward again, toward the edges of the cosmological canvas, where dark matter lurks. We cannot see it, but we feel its weight. Without it, galaxies like our Milky Way would tear themselves apart, stars flung into the void. Surveys of galaxy clusters show us that the majority of matter is unseen silent halos around galaxies, vast filaments in the cosmic web, structures that anchor the luminous islands of stars in space.
Even more enigmatic is dark energy, the silent accelerator that pushes galaxies apart. It permeates space itself, an invisible current stirring the cosmic sea, changing its destiny. Its nature remains obscure. Vacuum energy, a field yet unknown, a misread signal of gravity's breakdown on the grandest scales.
As you drift through these forces, gravitation, magnetism, quantum fluctuations, dark energy, you sense the unity hidden beneath. These are threads in a grand tapestry that connect the smallest subatomic world to the vast cosmic web, where monumental gravity collides with quantum whispers, where geometry and entropy meet. There lies the frontier of human understanding. And don't forget the cosmic microwave background, the oldest light. It carries within it minuscule ripples, seeds of every galaxy, cluster, and void. Its slight temperature variations map the ancient patterns laid down by inflation, perhaps hidden in those fluctuations lie the signatures of forces we have yet to comprehend, echoes from beyond our cosmic horizon. Your drift continues to the concept of cosmic topology, the global shape of the universe. If space is curved back on itself, you could travel light years in a straight line and return to your origin. haunted by echoes of your departure. Scientists are testing this by searching for repeating patterns in the cosmic microwave background, looking for the hall of mirrors that would reveal a finite, folded cosmos. Yet all of this, these waves, these fields, this dark scaffolding, these are stories of underlying structure. But what if structure itself is emergent? Some theoretical physicists suggest that space-time might not be fundamental at all, that it could arise from entanglement, information networks, or quantum bits. The fabric of reality could be a projection of more fundamental information patterns. If so, maybe what lies beyond the universe is not space, but the layer below networks of quantum entanglement, pre-space-time code from which our cosmos is woven. As the journey nears its current crest, you sense a subtle tension between what we know and what we can imagine. We've stepped from black hole mergers to vacuum fluctuations, from gravitational waves to cosmic topology. These elements are our atlas of the unknown, guiding both our instruments and our imagination. You float now at the intersection of matter and mind, where galaxies' grandeur meets the enigma of consciousness. Amidst the cosmic web's network of dark matter and radiation, life finds a foothold. Tiny, improbable sparks of organization in a sea of entropy. Molecules assemble into cells, cells into brains, and somewhere along that long journey, awareness awakens light piercing the dark from within. Think of a neuron in your brain, communicating through electrical signals. These firings are echoes of cosmic processes, waveforms traveling through fields, energy transferring along gradients. Within us, space-time and quantum rules collaborate to create a coherent self. Our perception is not separated from the universe. It is woven into the same fabric. But what does it mean to carry awareness in a universe written largely in mathematics and symmetry? Human minds have begun to translate the stars into equations, expressed the cosmic origin of matter in particle colliders, and glimpsed the early universe in snapshots of the cosmic microwave background. Our consciousness has become a lens, focused backward in time, letting us touch and perhaps shape the very moment of creation. Yet awareness also brings paradox. You understand that every structure from atoms to galaxies is subject to entropy. That complexity is temporary. Civilizations rise. Quasar jets light up once dead galaxies. Black holes decay. Conscious beings like us are fragile players in cosmic time. Our ephemeral spark begs the question, is intelligence just a flash, doomed to fade like a supernova, or part of something larger, something cosmic? If life is woven from cosmic threads, perhaps consciousness itself could be universal, an emergent property of certain complex systems under the right conditions. In that case, wherever the cosmos has organized matter into self-reflective patterns, whether under earthly oceans or distant exoplanets, there might be communities akin to ours, asking versions of these same questions. Imagine a distant intelligence that observes its cosmic microwave background, hears its own gravitational waves, surveys its dark, energy-dominated future, Perhaps they have mapped their cosmic topology, theorized multiple universes, or speculated on the holographic nature of reality. Yet, they may remain cut off from others by the event horizon, each consciousness stranded in its own observable bubble. That loneliness deepens the philosophical stakes. If every observer is confined to their local horizon, if space itself, and perhaps time itself, is fundamentally emergent, then each intelligence may be writing a story that starts and ends within its own bubble of space-time. Communication across these bubbles might be forever impossible, but the impulse to reach beyond, to decode the boundary, to uncover what lies outside our horizon, is a powerful testament to intelligence itself. It drives us to build space telescopes, to detect primordial gravitational echoes, to send messages into the void in the hope someone or something will listen beyond the cosmic horizon. None of us yet know whether those signals will ever find another listener. But the act of asking, of probing, deciphering, imagining may be the most cosmically significant thing a mind can do. In gazing outward, we reflect on ourselves. In seeking the origin, we confront our mortality. In tracing the fate of stars, we trace the fleeting arc of our own existence. So, as you settle into silence, picture the universe stretching behind you, ancient and vast. Then, picture yourself an observer born of quantum dust, casting a question across the cosmos. What lies beyond? The answer may be forever beyond reach, but the question matters. It binds us to the universe and to each other, and perhaps, in that shared wonder, lies a deeper kind of connection beyond space, beyond time, beyond all we know. Let this final note linger in your mind. Sleep gently closes around you. You have traveled across space-time's deep rifts, from inflation's birth to cyclic futures, from quantum voids to the emergence of awareness. You have touched the edge of the cosmic boundary and found not emptiness, but invitation. And in your question, the cosmos finds its echo.
Light takes 8 minutes to travel from the sun to Earth. That means everything we see in the sky is already in the past. Even the nearest star is not quite what it seems. Not in this moment. It is what it was. That idea is simple. Measurable is also profound. It means that when we look outward, we look backward. Every photon that reaches us is a silent witness from a different time. A cosmic delay is stitched into the very act of seeing. This delay is not trivial. A star 100 light-years away sent its light before the first electronic computers existed. Some galaxies shine from distances so great, their light began the journey long before our solar system formed. These aren't poetic metaphors. They are testaments to the scale of time and space we exist within. We see the present in our hands, but the sky shows us what is gone. A telescope is a time machine pointed up. Distances in kilometers collapse under the weight of this cosmic scale. What is 100 million kilometers to the sun when the nearest galaxy lies millions of light years beyond that? Traditional units become absurdly small. So we surrender them. Instead, we count in time seconds, hours, years of light. 1 light second is 300,000 kilometers. 1 light year is nearly 10 trillion kilometers. Our Earth, rotating and tilting modestly in its orbit, is wrapped in a bubble of delayed information. We do not see space, we see ancient signals. Yet with this simple conversion of distance into time, a remarkable clarity emerges. To say a galaxy is 10 million light-years away is to say we are witnessing it 10 million years ago. With every step farther outward, the universe reveals more of its youth. It's like peering through layers of sediment where deeper means older, and older means stranger. This is not just a scientific reality, it is a narrative structure written into the fabric of the universe. The farther you look, the more primal the story becomes. Even the scale of our own solar system, which seems vast, folds quickly under cosmic perspective. Light takes mere hours to cross from end to end, touching Pluto's orbit in about 10 hours. But then, to reach even the next star years, to leap to the stars beyond that centuries of light travel. Our Milky Way contains hundreds of billions of stars, each separated by spaces so wide the nearest neighbors are measured in parsecs, a unit born from trigonometric subtlety. Hold up a finger at arm's length, close one eye, then switch. The finger jumps. That is parallax, the change in perspective from two viewpoints. Astronomers use Earth's orbit as the arm's length, 1 astronomical unit wide. A nearby star seen in June will appear in a slightly different position 6 months later. From this shift, and the angle it creates, they calculate the distance. This method works well for stars a few hundred light-years away. Beyond that, the angle becomes too small. The stars sit too still. So astronomers reach for brightness. A nearby star's absolute brightness, known from parallax, becomes a candle to compare with more distant, similar stars. The dimmer a match appears, the farther it must be. But the light weakens with distance not linearly, but by the square twice as far is 4 times as faint. The universe does not give up its depth easily. Every measure is an inference. Every distance is reverse engineered from delay, dimness, and distortion. Beyond our galaxy, more galaxies float, millions of them. They form clusters and superclusters, stretching across the cosmos like veins in stone. Each is a swirling storm of stars, billions strong. These galaxies are not merely far, they are ancient. Their light began before life ever stirred on Earth. The space between galaxies makes even the vastness of the Milky Way seem intimate. Yet, within our own corner, stars show their secrets. Many are not solitary. They are paired, even tripled gravitational families orbiting one another in long, slow dances. Binary systems are common, and they vary wildly. Some stars orbit each other leisurely over decades. Others spin so closely they exchange matter, heat, and energy, shifting form and character over time. The sky is not quiet. It is teeming with motion, with evolution, with competition. The average distance between stars, about 1 parsec, is an enormous gulf. That's 20 million times the diameter of our sun. So despite the dazzling number of stars in the sky, they are scattered thinly across space, each lonely in its sphere, but their variety is endless. Stars differ in color, brightness, mass, and age. Their color reveals their temperature, and their brightness hides a story of size, heat, and internal fury. And imagine a star not as a point of light but as a globe of gas, suspended in nothing, held together by gravity and aglow with nuclear fire. The cooler stars burn red, the hotter ones, blue-white. Their placement in the Hertzsprung-Russell diagram, a map of stellar characteristics, traces a path from dim red dwarfs to blistering blue giants. The sun sits among the yellow-white, a modest beacon with a surface temperature of nearly 6,000 Kelvin. It is neither young nor old, neither large nor small, and yet the sun is the threshold. It is the standard by which others are judged. We speak of solar masses, solar luminosities. In that framework, some stars blaze with the force of 10,000 suns, others, white dwarfs and red dwarfs, whisper with faint, dying light. Some have surfaces as hot as 25,000 Kelvin, others linger near the threshold of fusion, barely radiating. A few are mere ghosts dense, dim remnants cooling over eons. The universe permits this diversity. It breeds it, encourages it, then watches as stars live, compete, and die. What we see in the sky is not static. It is history. It is rivalry. It is the consequence of physics unrolling across billions of years. And every glimpse we catch is shaped by the most fundamental truth of all: we are always looking into the past. The light that reaches us carries more than distance and delay. Encoded in every wave and photon is the temperament of the star that created it, its temperature, its rhythm, its weight. Most stars radiate steadily, but some flicker and swell like living hearts. These variable stars pulse in brightness, their outer layers expanding and contracting in cosmic breaths. The rhythm is not random. It is precise, often tied directly to a star's intrinsic brightness. Measure the pulse, and you know the power. Measure the power, and you know the distance. This relationship, first discovered by Henrietta Leavitt in the early 20th century, gave astronomers a tool as elegant as it is powerful. The longer a variable star's pulsation, the more luminous it is. By comparing that true luminosity with how dim it appears from Earth, we can measure its distance. These stars, called Cepheids, are among our most reliable beacons. They populate our galaxy and others, blazing like lighthouses across the sea of space. Some, like Polaris, throb gently, others vary more wildly, but each is a metronome in the dark, ticking out the depth of the cosmos. These Cepheids are not mere curiosities. They are evolved giants, larger and more massive than the Sun, nearing the end of their stellar lives. Their luminosity is tremendous, often thousands of times that of the Sun. They have passed through earlier stages of fusion, consuming hydrogen and now oscillating as their internal structures search for equilibrium. In these fluctuations, they sing, their surfaces ripple, their cores heave. The starlight flickers, but not in chaos. It flickers with the precision of a clock built in fire. Deeper inside the stars, away from surface rhythms, something more intimate occurs. A balance is constantly being negotiated. Gravity pulls inward, pressure pushes outward. For a star to exist, it must strike a perfect truce between collapse and explosion. The inner heat provides the pressure. That heat comes from nuclear reactions. Without them, the gravity would win. The star would fall in on itself and disappear. In the core of our Sun, the temperature reaches 15 million Kelvin. The pressure is so intense that gas behaves unlike any we experience on Earth. It is plasma fully ionized, with atoms stripped of their electrons. The particles move with furious speed, crashing into one another, generating radiation not in gentle visible light, but in harsh X-rays. That radiation does not stream freely to the surface. It is trapped, scattered, absorbed, and re-emitted endlessly, taking millions of years to escape. The light we see from the Sun today began its journey long before the first humans walked upright. This is not metaphor. It is delay built into the Sun's anatomy. The photons that finally emerge have bounced 1 trillion times through a crowded furnace of plasma. Only when they reach the convective outer layers can energy rise more swiftly, carried upward by boiling gas currents like water in a pot. In smaller stars, convection dominates. In larger ones, radiation carries more of the load. But in every case, the star finds a way to ferry its energy from core to surface and then into space. This energy flow is not silent. Inside the star, pressure waves move sound. In a sense, though not in air, these acoustic waves reflect and refract, creating complex standing patterns. Each star is a resonating chamber, humming with its own voice. In the Sun, these vibrations tell us about the interior we cannot see. Helioseismology, the study of solar sound, reveals the shape of its core, the depths of its convective zone, and the hidden churn of its layers. The Sun is not still. It rings like a bell. It hisses like steam. And those sounds, though silent to us, drive physical changes across its atmosphere. The outermost layers, known as the corona, are paradoxically hotter than the surface below, 1,000,000 degrees or more, heated by the chaotic flow of sound and magnetism. The thinness of the corona prevents it from radiating its heat away. Instead, it explodes outward, carried by charged particles in what we call the solar wind. This stream of gas flows through the solar system, shaping planetary atmospheres, buffeting magnetic fields, and whispering to every satellite and probe. Other stars possess their own stellar winds, some gentle, others savage. A few are so intense they tear the stars apart over time. Gas flows away in rivers, accelerated by radiation and magnetism. In some stars, the shedding is slow and sorrowful. In others, it is a tempest. The universe does not mandate serenity. Some stars live like monks. Others die in flames. Yet all of them are powered by the same fundamental engine, nuclear fusion. At its heart, a star is a reactor. It fuses hydrogen into helium, converting mass into energy. But this process is not simple. Protons are positively charged. They repel each other. To fuse, they must come unimaginably close, even in the center of the sun, with temperatures soaring and particles speeding. Most collisions do nothing. Only occasionally 1 in a trillion does quantum tunneling allow a proton to sneak past the barrier, to touch, to fuse. This is the first of 2 great hang-ups. The second is subtler. Even when 2 protons meet and bond, they must transform. 1 proton must become a neutron. This requires a weak nuclear interaction, an unlikely quantum event. On average, a proton in the sun's core waits billions of years to undergo this change. But there are so many protons that some are always reacting, keeping the fire alive. Fusion releases energy because the helium nucleus that results is slightly less massive than the 4 protons that formed it. The missing mass becomes energy, flung outward as heat and light. The process is known as the proton-proton chain. In larger stars, a more complex cycle dominates the carbon-nitrogen-oxygen cycle, or CNO. It is less dependent on quantum chance and more efficient at higher temperatures, but all fusion in stars has the same goal: transform mass into energy, and in doing so, resist collapse. The stars are not static. They are not simple. They are delicate balancing acts, held between gravity and radiation, between collapse and expansion. They are ancient engines wrapped in fire, whispering across the cosmos through light and sound. And yet, even they have lifetimes. Their fuel is not infinite. Their patience runs out. And when it does, something else begins. A star's death begins in silence. Its core, having spent millions or billions of years transmuting hydrogen into helium, reaches a point of exhaustion. The fire wanes not everywhere, but in the heart where fusion once blazed cleanly and steadily. What remains is a cinder of helium, hot and inert. The outer layers, still glowing, still shedding light, no longer draw energy from within. The balance tilts. Gravity, ever patient, resumes its slow encroachment. The core contracts. In falling inward, it releases gravitational energy, heating the surrounding layers. A shell of hydrogen outside the core begins to burn, reigniting in a fury that pushes the outer envelope outward. The star swells, its surface cools. It becomes a red giant. The transformation is not immediate, but when it comes, it is dramatic. A star that once shone with a steady yellow-white glow now glows red and vast. It becomes luminous not by raising its temperature but by expanding its surface. It is no longer a quiet main-sequence star. It is bloated, unstable, nearing the end. For lower-mass stars, those similar to or smaller than the Sun, this is the final phase of grandeur. The core, composed of helium, contracts further, When the temperature crosses 100 million Kelvin, helium ignites in a flash. Not an explosion, but a rapid runaway fusion event. Helium fuses into carbon and oxygen. The flash stabilizes the core for a time. A new balance is struck. The red giant stabilizes, if only briefly. The envelope is now tenuous. A strong stellar wind builds, driven by both radiation and pressure. The star begins to shed its outer layers. Shells of gas drift away into space, lit by the remaining core like lanterns in mist. What remains is a white dwarf, a naked core, hot and small, about the size of Earth. It no longer burns fuel, it merely cools, radiating away the last heat of its long life. The white dwarf is dense. A teaspoon of it would weigh tons. And yet it shines, dimly, for billions of years. The sun will become such a relic. In 5 billion years, our star will cast off its atmosphere and rest as a pale white ember, glowing faintly in the twilight of time. But for stars with greater mass, the ending is far more violent. They burn through hydrogen quickly, then helium, then heavier elements. The core becomes layered, like an onion, each shell fusing a different element. Carbon to neon, neon to oxygen, oxygen to silicon, silicon to iron. With each new fusion process, the temperature and pressure rise. But there is a limit. Iron is that limit. Fusing iron does not release energy, it consumes it. When the core fills with iron, the engine stalls. The outward pressure of radiation disappears. Nothing holds gravity back. Collapse begins. The core falls inward in milliseconds. Electrons are crushed into protons, forming neutrons. The matter becomes incompressible. The collapse halts abruptly, and the rebound sends a shockwave outward. In that instant, neutrinos, those ghost-like particles, pour out in vast numbers, carrying away energy. The shockwave, assisted by this sudden flood, tears through the star, blowing off its outer layers in a colossal detonation, a supernova. For a brief time, the star outshines its entire galaxy. A supernova near Earth would cast shadows at night. It would be as bright as the full moon. The explosion spreads heavy elements, carbon, oxygen, gold, uranium into space. These are the seeds of new stars, new planets, and eventually, new life. We are built from this wreckage. The iron in our blood, the calcium in our bones, the carbon in our cells, all forged in stellar death. What remains after such an explosion depends on the mass that was left behind. If the remnant is less than about 3 times the mass of the sun, the core stabilizes as a neutron star. Imagine a city-sized sphere, 10 kilometers across, denser than anything else in the universe apart from black holes. A thimble of neutron star matter would outweigh a mountain. The surface gravity is so immense that any object dropped from a centimeter above would strike with the force of a bomb. Neutron stars often spin rapidly, their magnetic fields sweeping through space. These rotating beacons are called pulsars. With each turn, they emit a pulse of radiation like the beam of a lighthouse. Some spin hundreds of times per second, a blur of dense matter trapped in an eternal twirl. But if the remnant is more massive still, not even neutron degeneracy pressure can halt the collapse. The core continues falling. There is no force in nature strong enough to stop it. The result is a black hole. This is not just an object. It is a boundary in space and time. Beyond the event horizon, nothing escapes, not light, not sound, not thought. The core collapses into a point of infinite density, a singularity. Around it, space is warped beyond comprehension. Time itself slows as you approach. To fall into a black hole is to vanish from the universe's visible story. Your final light stretched and reddened until it fades into silence. Black holes do not roam freely, devouring stars at random. They obey gravity like any other mass. But when they do feed, the process is spectacular. Matter spirals inward, heating to millions of degrees, emitting X-rays and gamma rays. In some cases, vast jets erupt from the poles, carving cavities in the interstellar medium. The feeding is not quiet. It is theatrical, violent, luminous, beyond understanding. The star is gone. The fusion is over. But its legacy persists in the debris scattered across light years, in the elements scattered through future generations of stars, in the silent core that endures as neutron star or black hole. Every galaxy is shaped by such events. Every planet owes its material to the ghosts of long-dead suns. A star's life is long and quiet. Its death is brief and cataclysmic. And in that ending, the seeds of new worlds are born. In the darkness between the stars, clouds of gas drift silently, great volumes of hydrogen and helium, tinged with traces of heavier elements. For eons, they remain quiet, cold, featureless. But within these vast expanses, gravity begins its slow, relentless whisper. Slight imbalances, perhaps triggered by a passing shockwave from an ancient supernova or the subtle tug of a neighboring cloud, set particles into motion. Denser regions collapse inward, drawing in more mass. The process accelerates. The cloud fragments. Each fragment forms a rotating globule, an embryo of a future star. These protostars, cloaked in veils of dust, cannot yet be seen in visible light. They glow faintly in infrared, heat building as gravity compresses their hearts. The core tightens, pressure climbs, temperature rises. But for millions of years, there is no fusion. The heat is gravitational, a furnace built on falling. As the protostar contracts, it begins to spin faster. This is not by choice, but by law. Angular momentum conserved as mass collapses. The spinning disk around the protostar flattens and spreads, forming the stage for the next act, the birth of planets. Within the disk, dust grains coalesce. Minute collisions build larger clumps. The game is not fair. The biggest grow faster, drawing in smaller bodies. What begins as scattered dust becomes a chaos of tumbling rock and ice, each fragment following its own orbit, some spiraling inward, others flung outward. Over time, gravitational dance favors the few. Planetary embryos emerge, planetesimals the size of mountains, then continents. Some collide and shatter, others merge. Those that endure become protoplanets, their paths more circular, their mass sufficient to shape themselves into spheres. Gas giants form farther out, where cold temperatures allow volatile gases to condense. These massive worlds draw in hydrogen and helium, growing rapidly, their cores cloaked in deep atmospheres. Closer to the star, where heat drives gases away, terrestrial planets remain barren, rocky, fragile. In the heart of the system, the protostar finally reaches the threshold. Its core crosses 10 million Kelvin. Hydrogen ignites. Fusion begins. A balance is struck, the inward pull of gravity matched by the outward push of energy. The star is born. The sun awakens. Its fierce light sweeps away the remnants of the gaseous cloud, pushing back against the birth materials that formed it. The radiation and solar wind clear out debris, shaping the remaining architecture of the system. The planets that survive do so at the whim of this stellar tantrum, and their fate is sealed in the geometry of their orbits. In the early chaos, impacts are frequent. The inner solar system becomes a battlefield. Asteroids and comets bombard the young Earth. Some bring water, others sterilize the surface with fire. The scars remain in cratered moons, in tilted axes, in odd orbital resonances. A late, great impact tears a chunk from Earth's side. The debris coalesces into a satellite, the Moon. Its presence stabilizes Earth's rotation, sets tides in motion, and locks our planet into a rhythm that will nurture future life. After a few 100 million years, the bombardment slows, the solar system settles, the planets spin quietly in their orbits, moons circle planets, and the sun shines with steady brilliance. But the sun is not still. Its surface roils with convection. Magnetic storms arc into space. The solar wind continues, an eternal gale of charged particles streaming outward, touching every planet and pressing against the interstellar void. The sun's light takes 8 minutes to reach Earth. The signals we receive from its surface are already history. What we see is not what is, it is what was. This delay in light is not unique to our star. It is the universal consequence of speed and distance. Every point in the sky is a museum of the past. The farther we look, the older the image. A galaxy 10 million light-years away appears as it was 10 million years ago. We are surrounded not by objects in the present, but by echoes, fossils of light. Distance and time are entwined. To observe deeply is to peer into history. A telescope is a time machine, and the night sky is a window into moments that have long since passed. The nearest stars are light-years away. Their parallax, the slight shift in apparent position as Earth moves around the sun, gives us a measure of their distance. Beyond a few hundred light-years, even this shift is imperceptible. We must rely on luminosity, color, and spectral fingerprint to guess their remoteness. The stars themselves vary immensely. Some are red dwarfs, dim and enduring, destined to burn for trillions of years. Others are massive blue giants, burning so hot and fast they perish within a few million years. Most stars, like the sun, are main sequence a band on the Hertz-Sprung-Russell diagram that reveals a simple truth: a star's mass determines its fate. The diagram itself is no mere chart. It is a map of stellar life, from the dim and cool to the hot and brilliant. It lays out the stellar population in patterns that hint at hidden laws. The main sequence, the red giants, the white dwarfs, each region tells a story, not just of temperature and brightness, but of origin and destiny. The stars are not randomly placed. They cluster, drift in families, rotate around galactic centers. Many are not solitary. Binary systems are common: two stars locked in orbit, some distant, others so close they transfer mass, their evolution intertwined. Some binaries merge, igniting new flares of energy. Others erupt in nova or end in shared collapse. In rare cases, one devours the other. Their stories are many. Their silence conceals the violence beneath. What we call a star is a process, not a product. A balance of forces, a furnace of nuclear fire, a beacon that writes its own biography in light. Each flicker across the night sky is a whisper from a distant forge, a statement of physics, chance, and endurance. And each of these whispers arrives late, trailing behind the moment of its making, forever separated from the now by the span of space and time. Inside the quiet skeleton of a dying star, the fire of creation meets its limits. Hydrogen, once abundant and obedient, is long gone from the core. Helium, too, has fused into heavier elements: carbon, oxygen, silicon. What remains is a complex, layered relic, like an onion of atomic ancestry, each shell burning a different fuel, each closer to collapse than the last. The fusion reactions, which once staved off gravity, now accelerate with desperation. In the final days, a massive star can burn through silicon in mere hours, producing iron, a dead end in nuclear alchemy. Iron neither gives nor takes energy through fusion. It is inert, the ash of the stellar flame. The core grows heavy with it. Its weight, no longer countered by outward pressure, begins to pull inward, faster than sound can escape, faster than the atom can respond. The iron heart collapses. Electrons slam into protons, forming neutrons. In an instant, a city-sized core becomes a neutron star. Above it, layers of gas fall inward like a city crushed by gravity. But the core resists. The infall halts, rebounds. An enormous shockwave bursts outward, ignited by a flood of neutrinos, the ghost particles of the universe pouring from the newborn neutron core in numbers beyond comprehension. The star explodes, A supernova lights the galaxy, outshining billions of suns. Its brilliance lasts only weeks. But in that moment, it sears itself into the cosmos, the elements forged in its interior gold. Uranium, iodine scatter into space. Dust enriched by the dead becomes the seeds of the living. The remnants of the star vary by mass. If the core is under the limit about 3 times the sun's mass, it settles as a neutron star. A thimbleful of its matter outweighs mountains. Its magnetic field is 1 trillion times stronger than Earth's. It may rotate hundreds of times per second, sending pulses of radiation across space, a lighthouse in the void. We call them pulsars, these trembling fossils. They speak not in words, but in timing perfect, mechanical, mournful. Each beat carries memory. Each signal is the echo of collapse held in exquisite rhythm. But if the core is heavier still, even neutrons are crushed. Nothing can resist the final fall. Space itself curves inward. Light cannot escape, and the star becomes invisible, a black hole. This term, so soft in sound, masks what it means. A black hole is not a thing, but a boundary. A cliff in space-time beyond which no return is possible. It is a wound in the structure of reality, the place where time stops making sense. Surrounding the black hole is the event horizon, the point of no return. Outside it, time moves forward. Inside, all futures lead to the singularity, a place where density becomes infinite and physics loses its voice. We do not know what lies at the singularity. Our equations scream with infinities and contradictions. General relativity bends. Quantum mechanics fractures. It is the edge of knowledge, the end of prediction. Black holes grow by swallowing. They devour stars, gas clouds, other black holes. At galactic centers, they sit like monarchs, invisible yet ruling. Some weigh millions or billions of solar masses. Their gravity sculpts the movement of stars, shapes galaxies, triggers jets of matter and energy that stretch across intergalactic space. They are silent architects of cosmic order, formed in violence, living in shadow. And yet, not all end in collapse. Lesser stars walk gentler paths. If born with low mass, they shine steadily for tens of billions of years, fusing hydrogen slowly, living longer than the current age of the universe. When their hydrogen is gone, they swell into red giants, shed their outer layers into space, and settle as white dwarfs. These stellar embers, roughly Earth-sized, glow faintly for eons. Some may eventually cool into black dwarfs. Though the universe is still too young to have produced any, they are the final breath of stars too small to die with thunder. In some binary systems, white dwarfs steal matter from a companion. When enough accumulates, a thermonuclear runaway occurs. The star explodes in a Type Ia supernova so consistent in brightness that it serves as a cosmic milepost, measuring the universe's expansion. There are other signals of distance, too, Cepheid variables, massive stars that pulse rhythmically, grow brighter and dimmer over predictable cycles. Their period tells us their true luminosity. Comparing this to their apparent brightness reveals how far away they are. Light, again, is the courier of truth. Our knowledge of the universe is built from what arrives on waves of light and particles of ghostly origin. Neutrinos from supernovae, gravitational ripples from colliding black holes, shadows cast by galaxies, spectra of starlight. Even the silent vacuum speaks. The cosmic microwave background relic radiation from the birth of the universe saturates space. A whisper from 13 billion years ago. Its pattern tells us the shape of space, the fate of time, the balance of matter and dark energy. And so we orbit, this Earth spinning beneath a star that will someday swell, burn its hydrogen to helium, shed its skin, and leave behind a white dwarf. Long after we are gone, it will remain, dimming slowly. Around it may still circle the ghost of what was a system shaped by violence and decay, but also by balance, emergence, and radiance. The universe, for all its harshness, is not a place of pure entropy. It is a realm where structure can rise from chaos, where time does not just erode but reveals. Every star carries a story written in heat and pressure, forged in collapse and light. Every planet is a testimony to improbable assembly, a relic of gravitational games. And every life that gazes skyward becomes part of this unfolding epic, finite, fragile, yet curiously aware of the infinite beyond, in the cold spaces between galaxies, in the dark hearts of dying stars. In the minute reactions of subatomic particles there are echoes, not just of matter and energy, but of questions, of silence interrupted by light, of time made visible. The story never ends. It only fades beyond the horizon, into the vastness from which it came.
In the depths of space, 13 billion light-years from Earth, astronomers have discovered something that should not exist. Galaxies so massive, so perfectly formed that they appear older than the universe itself. These cosmic giants, glowing like ancient cities in the darkness, contain as many stars as our own Milky Way. But they formed when the universe was supposedly just a newborn infant, barely 500 million years old. We will journey through impossible discoveries that are shaking the foundations of science, encounter galaxies that defy the laws of physics, and explore theories that could double the age of everything we know. The James Webb Space Telescope has not just changed what we see in space. It has potentially shattered our most fundamental beliefs about reality itself. Prepare yourselves. July 11th, 2022, changed everything. Scientists around the world received the first images from the James Webb Space Telescope, expecting to see the cosmic equivalent of baby photos. They were prepared for faint, ghostly protogalaxies, disorganized smudges of light from the universe's earliest morning. Instead, they found giants. Dr. Erica Nelson stared at her computer screen in disbelief. The tiny red dot she was analyzing should have been a faint smudge, a primitive galaxy struggling to form its first stars. But the numbers her software calculated made her nearly spill her coffee. The distance was 13.1 billion light-years, meaning she was looking at an object as it existed when the universe was a mere 700 million years old. Yet the mass was 100 billion stars. This was not a fledgling cosmic village. It was a sprawling, mature metropolis, a galaxy containing as many stars as our entire Milky Way. Think of it like finding a fully grown oak tree in a nursery full of seedlings. It was an affront to the smooth, elegant narrative of creation that cosmology had spent a century building. According to everything we know about how galaxies form, this should be impossible. The Big Bang Theory, our most successful model of the universe, tells us that after creation 13.8 billion years ago, it took hundreds of millions of years for the first stars to ignite. Those first stars, primordial giants made of pure hydrogen and helium, then had to live, die, and scatter heavy elements across space before the next generation could form. Building a galaxy like the Milky Way should take billions of years of this cosmic recycling, a slow, patient process of gravitational accumulation and stellar alchemy. It is a story of generations, where each epoch builds upon the ashes of the last. But here was a galaxy that appeared to have skipped the entire process. It glowed with the light of ancient, evolved stars, showed complex structure with a dense central bulge and a flattened disk, and contained the chemical fingerprints of heavy elements that should not have existed yet. The discovery did not just bend the rules, it violated the fundamental timeline of cosmic evolution. If the universe was only 700 million years old at that point, where did this galaxy find the time to grow so massive? Where did it find the raw material? How did it forge the complex elements that painted its light with the colors of maturity? The implication sent shockwaves through the scientific community. Not with a loud crash, but with a quiet, persistent hum of cognitive dissonance. The map no longer matched the territory. Either our understanding of galaxy formation was completely, fundamentally wrong, or the universe itself was much older than we thought. Some researchers began whispering about the unthinkable, that the Big Bang theory, the bedrock of modern cosmology, might need to be reconsidered, or at least radically revised. The elegant clockwork of the cosmos had a broken gear. Dr. Nelson and her colleagues had stumbled upon what would become known as the impossible early galaxy problem. Within months, similar discoveries multiplied across the sky. Webb's unblinking eye found more of these cosmic paradoxes, each new find deepening the mystery and challenging the foundations of our cosmic story. But this single red dot was just the beginning of a puzzle that would force humanity to question everything we thought we knew about the universe's birth, its age, and its very nature. The universe operates on a cosmic schedule that seemed unbreakable until now. According to the standard Big Bang model, the first 400,000 years after creation were a period of blinding chaos. A hot, dense soup of particles and radiation where not even atoms could form. The entire cosmos was an opaque fog, a furnace of unimaginable temperature. Only after this cosmic fog cleared, an event known as recombination, could hydrogen and helium atoms finally assemble. For the first time, light could travel freely through space, and the universe became transparent. But this new clarity revealed a profound darkness. The cosmic dark ages had begun. These simple elements, hydrogen and helium, drifted through space for another 100 million years in a vast, silent expanse, devoid of stars or galaxies. Gravity, the patient sculptor of the cosmos, then began its slow work. It pulled these primordial gases together into massive clouds, the first stellar nurseries. Those primordial stars, massive and short-lived giants known as population 3 stars, had to live out their brief, violent lives and explode as supernovae to create the first heavy elements, like carbon and oxygen. These are the elements essential for rocky planets, for complex chemistry, for life itself. Only then, after these stellar titans had seeded the cosmos with their ashes, could the next generation of stars begin forming the complex galaxies we see today. This entire process, from the first atoms to the first mature galaxies, should take at least 1 billion years, and likely much longer. It is like building a skyscraper from the ground up. You need a foundation of primordial gas, then a framework of the first stars, then the floors built from the recycled materials of those stars, and finally, the finishing touches of complex chemistry and stable structures. The universe supposedly followed this same step-by-step construction process. But the galaxies Webb discovered seem to have completed this entire construction project in half the time, or less. They contain heavy elements that should not exist yet, stars that should not have had time to form, and organized structures that should not have had the opportunity to settle. It is as if someone built a cathedral, with all its intricate stonework and stained glass windows, in a single afternoon. The numbers simply do not add up. If the universe began 13.8 billion years ago, and we are seeing these galaxies as they were 13.1 billion years ago, that leaves a mere 700 million years for them to form. Our best physical models suggest they would need at least 2 billion years, and more likely 5 to 6 billion years, to reach such massive sizes and chemical maturity. This timing problem, this cosmic paradox, has forced astronomers to consider three possibilities, each more revolutionary than the last. First, galaxy formation might work in a completely different way than we thought, with stars forming perhaps 100 times faster than our current models predict. This would require new physics, a way to bypass the natural feedback mechanisms that regulate star birth. Second, the universe might be much older than 13.8 billion years, giving these galaxies the extra time they need to mature gracefully. This would mean our measurement of the cosmic expansion rate, the very foundation of the Big Bang model, is wrong. Third, and most radically, the Big Bang theory itself might be fundamentally flawed or incomplete. The cosmic clock is ticking, and something does not match the schedule we thought was written in the stars. The ground beneath our understanding of cosmic history is beginning to crumble. Among the thousands of galaxies Webb photographed, one particular type stood out like mysterious beacons in the primordial darkness. Astronomers dubbed them little red dots, because that is exactly what they appeared as: tiny, intensely crimson points of light, completely invisible to previous telescopes like Hubble. These red dots became the smoking gun in cosmology's greatest mystery, the irrefutable evidence that something was deeply wrong with our story of the universe. Unlike normal galaxies that shine across a broad spectrum of colors, these objects glowed intensely in infrared light while remaining nearly invisible in other wavelengths. This extreme redness suggested they contained something extraordinary, something that defied the conventional wisdom about the early cosmos. The color could be caused by one of two things. Either they were filled with ancient, cool, red stars, or they were shrouded in immense clouds of dust, which absorbs blue light and lets red light pass through. When scientists analyzed the first of these red dots, the one discovered by Dr. Nelson's team, they found it contained roughly 100 billion stars, making it comparable in mass to our own Milky Way. But this galaxy existed when the universe was only 5% of its current age. The discovery was like finding a fully grown, gray-haired human in a nursery full of newborns. It was a temporal impossibility. The red color itself told a story that challenged everything we knew about early cosmic evolution. In a young universe, galaxies should be overwhelmingly blue and bright, filled with hot, massive, young stars that burn through their fuel quickly and violently. Red galaxies, in our modern universe, typically indicate old, mature stellar populations, stars that have been burning steadily for billions of years, their hot blue giants long since extinguished. But these red dots appear to be both young and old simultaneously. They existed in the early universe, which makes them young by definition. Yet they contain the stellar signatures of ancient, evolved systems. This paradox violated the basic principles of cosmic evolution, like finding snow in the heart of summer. As more red dots appeared in Webb's deep field images, the pattern became undeniable. These were not isolated anomalies or measurement errors. They were part of a larger, previously unseen population of massive early galaxies. Some estimates suggested there were 100 times more of these objects than the standard Big Bang theory predicted should exist. The scientific community split into camps, each proposing a different solution to the riddle. Some researchers argued the red dots were proof that galaxy formation was far more efficient and rapid in the early universe than anyone had imagined. Perhaps the physics of star birth was different in the dense, hot environment of the primordial cosmos. Others suggested the dots were optical illusions, their intense redness and apparent mass created not by stars, but by actively feeding supermassive black holes at their centers, outshining their host galaxies. But a growing number of scientists began to consider a more radical possibility that the red dots were telling us something fundamental about the universe itself was wrong. That our cosmic clock was broken, and these ancient-looking galaxies were exactly what they appeared to be old. Inside every galaxy, stars are born from vast, cold clouds of gas and dust in a delicate process that normally takes millions of years. But the massive early galaxies Webb discovered seem to have compressed this entire timeline into something almost impossible. To create a galaxy with 100 billion stars in only 700 million years, star formation would need to occur at a rate that defies known physics. A furious, non-stop storm of creation. Current models of galaxy evolution suggest that even under the most perfect conditions, galaxies can only convert about 10% of their available gas into stars in a given period. The rest gets blown away by the powerful radiation of stellar winds and the explosive shock waves of supernova explosions. This process acts as a natural feedback loop, a cosmic thermostat that regulates the pace at which new stars can ignite. But these early giants appear to have achieved conversion rates approaching 100%. To do this, every single atom of hydrogen and helium within their gravitational grasp would need to have been transformed into stars with almost no waste. This is like expecting a factory to operate at perfect efficiency, with zero defects, zero leftover materials, and zero downtime. It is a theoretical ideal, not a physical reality. The energy requirements alone seem insurmountable. When massive stars form, they generate powerful stellar winds and intense ultraviolet radiation that heat the surrounding gas to millions of degrees. This hot gas normally expands and escapes from the galaxy, preventing further star formation. It is a self-limiting process. For these early galaxies to form so many stars so quickly, they would need to have somehow overcome this natural cooling process. They would need a way to keep their star-forming fuel trapped and cold, even in the face of a stellar firestorm. Some scientists propose that the early universe was much denser, making it harder for hot gas to escape the gravitational pull of a young galaxy. Others suggest that the enigmatic dark matter behaved differently in the primordial cosmos, providing stronger, deeper gravitational wells to trap the star-forming material and shield it from the disruptive energy of young stars. The mathematics of such rapid star formation pushed the boundaries of theoretical physics. Computer simulations that attempted to recreate these conditions either failed to produce enough stars or created galaxies that should have torn themselves apart from their own internal energy output. The models kept breaking under the strain of the observed reality. Yet the evidence from Webb was undeniable. These galaxies had somehow achieved star formation rates that modern physics said were impossible. They had compressed billions of years of cosmic evolution into a few 100 million years. Like watching a time-lapse video of galactic development playing on fast forward. The implications reached far beyond astronomy, suggesting that our understanding of some of the most fundamental processes in the universe might require a complete and radical revision. At the heart of every massive galaxy we know lies a supermassive black hole. A gravitational monster containing millions or even billions of times the mass of our sun. But in the early universe, these cosmic giants present an even greater mystery than the galaxies they inhabit. The red dots Webb discovered do not just contain impossible numbers of stars, they also appear to harbor black holes that grew too big, too fast. These objects show the telltale signatures of actively feeding black holes, with surrounding gas spiraling inward at tremendous speeds and heating to millions of degrees. This process creates some of the brightest objects in the universe, phenomena known as quasars. But growing a supermassive black hole takes time. It is like feeding a cosmic beast that can never be satisfied. A black hole must consume vast quantities of gas, dust, and stars from its surroundings to grow. And there are physical limits to how fast it can feed. Scientists call this the Eddington limit, the maximum rate at which matter can fall into a black hole before the outward pressure from the heating gas balances the inward pull of gravity. It is a natural safety valve that prevents a black hole from eating too quickly. Even if a black hole fed continuously at this maximum rate, day and night for its entire existence, it would still take hundreds of millions of years, if not billions, to grow from a stellar mass seed, the remnant of a dead star, to supermassive proportions. But the black holes Webb found appear to have achieved this monumental growth in a fraction of the available time. Some of them would need to have been feeding at 5 times the Eddington limit, or more, for their entire existence. This is like discovering that someone gained 1,000 pounds by eating only one small meal per day. The physics simply does not allow for it. Yet, these primordial black holes seem to have violated the fundamental laws governing their own growth. They are too massive for their age, too well fed for the cosmic pantry that should have been available to them. The problem becomes even more complex when considering where these black holes came from in the first place. The traditional model suggests they formed from the collapse of the first generation of massive stars. But those stars would need time to form, live out their short lives, and die before leaving behind the black hole remnants. In the early universe, this process alone would consume most of the available time, leaving very little opportunity for the subsequent, slow growth phase. Some researchers now propose a more dramatic origin story, that supermassive black holes might have formed directly from the collapse of massive primordial gas clouds, skipping the stellar phase entirely. Others suggest that the early universe contained mysterious, hypothetical objects called primordial black holes, formed in the chaos of the Big Bang itself, which could have served as massive seeds for later, accelerated growth. But whatever their origin, these cosmic monsters were about to reveal an even more shocking secret about the nature of reality itself. What if the most massive galaxies Webb discovered were not massive at all, but cosmic magicians performing the ultimate illusion? Recent research suggests that some of these early giants might be optical mirages, their incredible brightness and apparent mass created not by stars, but by the very black holes at their centers. When matter falls into a supermassive black hole, it forms a swirling, incandescent disk called an accretion disk. Friction within this disk heats the material to millions of degrees, causing it to glow with a light brighter than billions of stars combined. This intense radiation can completely outshine the entire galaxy surrounding the black hole, creating a false impression of tremendous stellar mass. The effect is like trying to count the number of candles in a room while someone shines a powerful searchlight directly into your face. The overwhelming brightness of the searchlight makes it impossible to see the faint candlelight underneath. Similarly, these actively feeding black holes, or quasars, can mask the true stellar content of their host galaxies, making them appear far more massive and mature than they actually are when viewed through Webb's infrared eyes. This discovery offered a potential, elegant solution to the impossible early galaxy problem. If many of the red dots were actually moderate-sized galaxies with extremely bright central black holes, then the crisis in cosmology might be resolved. The universe would not need to violate the laws of physics to create massive galaxies in record time. It would only need to create massive black holes. But this explanation came with its own set of thorny problems. Even if the galaxies were less massive than they appeared, they still contained supermassive black holes that should not exist in the early universe. The mirage hypothesis simply moved the impossibility from the stellar mass to the black hole mass. the fundamental timing problem remained. Furthermore, detailed spectroscopic analysis of some of the red dots showed clear evidence of large, established stellar populations alongside the signatures of the black holes. These galaxies were not just bright, they were genuinely massive, containing billions of stars that had somehow formed in the cosmic blink of an eye. The mirage effect might explain some of the Webb observations, but it could not account for all of them. Many of the early galaxies appeared to be both massive and bright, suggesting that the universe had indeed found a way to accelerate cosmic evolution beyond our current understanding. The illusion was not total. The reality was just as puzzling. As astronomers worked tirelessly to separate the genuine giants from the cosmic illusions, an even more radical possibility began to emerge from the shadows of scientific history. A forgotten theory that threatened to rewrite the entire story of the cosmos. In 1929, while Edwin Hubble was discovering that distant galaxies appeared to be racing away from us, a brilliant and eccentric Swiss astronomer named Fritz Zwicky proposed a radically different explanation for the same observations. What if the galaxies were not moving at all? But light itself was changing as it traveled through the vast emptiness of space. Zwicky's idea, which he dubbed tired light, suggested that photons, the particles of light, gradually lose energy during their long journey across the cosmos. As light loses energy, its wavelength increases, shifting it toward the red end of the spectrum. This redshift would make distant galaxies appear to be receding from us, when in reality, they could be stationary in a static, unchanging universe. The tired light theory offered an elegant, if unconventional, alternative to the expanding universe model. Instead of space itself stretching and carrying galaxies along for the ride, the cosmos would be eternal and unchanging. The redshift we observe would simply be a natural consequence of light aging during its billion-year journey to our telescopes. For decades, the tired light theory remained on the fringes of cosmology, dismissed by most scientists due to several observational problems that it could not adequately explain. The theory struggled to account for why distant supernovae appeared to last longer than nearby ones, a phenomenon perfectly explained by time dilation in an expanding universe. Nor could it provide a convincing origin for the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space. But the James Webb discoveries, with their impossible timelines and mature-looking galaxies, have breathed new life into this forgotten theory. If the universe is not expanding, then the redshift of distant galaxies is not an indicator of their velocity or their age relative to us. We would be seeing them at their true age, which could be billions of years older than the Big Bang model predicts. This would provide more than enough time for massive galaxies to form without violating the known laws of physics. The ancient cities of the cosmos would be exactly that ancient. Recent studies have attempted to revive and modernize this idea, combining the tired light concept with subtle changes in fundamental physical constants over time. This hybrid model, while still highly speculative, suggests the universe could be as old as 26.7 billion years, nearly twice the age predicted by standard Big Bang cosmology. In this ancient cosmos, even the most distant galaxies Webb has observed would have had billions of years to assemble their massive stellar populations, grow their supermassive black holes, and enrich themselves with heavy elements. The tired light resurrection represents more than just an alternative theory. It challenges the very foundation of modern cosmology and our understanding of time itself, suggesting that the cosmic story we have been telling ourselves for the past century might be built on a fundamental misinterpretation of the light from distant stars. What if the fundamental constants of physics, the unchanging numbers that govern how matter and energy behave, were not constant at all. Recent research, spurred by the Webb discoveries, suggests that the speed of light, the strength of gravity, and other supposedly fixed parameters might have been different in the early universe. This radical idea emerged from attempts to reconcile Webb's impossible galaxies with the known laws of physics. If the fundamental constants were variable, then the early universe might have operated under a completely different set of rules than it does today. Stars could have formed much faster. Black holes could have grown more rapidly, and galaxies could have assembled in a fraction of the time we previously thought necessary. The concept of changing constants is not entirely new to physics. Some theories of quantum gravity and string theory suggest that the fundamental parameters of the universe might evolve as it ages. But applying this idea to solve the problems of cosmology requires a precise and delicate fine-tuning, like adjusting the hidden knobs on a cosmic radio to find the exact frequency where everything makes sense. One proposed model combines these variable constants with the tired light theory to create a universe that is 26.7 billion years old. In this scenario, the early cosmos had different physical laws that allowed for the rapid formation of galaxies, while the tired light mechanism explains the redshift we observe today without requiring the expansion of the entire universe. The mathematics are elegant, but deeply controversial. Critics argue that changing the fundamental constants would have wide-ranging effects on many other observable phenomena. From the precise temperature of the cosmic microwave background to the synthesis of light elements in the first few minutes after the Big Bang. The theory would need to explain why these constants changed in exactly the right way to match all of our current observations, a task of immense complexity. Supporters of the idea counter that our current understanding of physics is clearly incomplete, and that the Webb discoveries are a clear sign that we need new theoretical frameworks. They point out that the standard model of cosmology already requires the existence of mysterious, unexplained entities like dark matter and dark energy to make sense of observations. In that context, the idea of variable constants might be no more radical than the accepted mysteries we already live with. The debate over inconstant constants reflects a deeper, more philosophical question about the nature of scientific truth. Are the laws of physics truly universal and eternal, written in stone since the beginning of time? Or do they evolve, adapt, and change along with the cosmos they govern? As scientists grapple with these profound implications, the galaxies Webb discovered continue to shine down from the distant past, challenging our most basic assumptions about the stability and predictability of reality itself. Faced with observations that seem to break the very laws of physics, astronomers turn to their most powerful tool, computer simulations. By creating digital universes inside supercomputers, they could model the birth and evolution of galaxies across cosmic time. These digital experiments would either confirm the stark impossibility of the early massive galaxies or reveal a hidden pathway, a new physical mechanism by which nature might have achieved the seemingly impossible. The first simulations, run with the standard, accepted physics, painted a grim and unyielding picture. No matter how they tweaked the initial conditions, the computer models could not create the cosmic giants Webb had discovered. The simulations consistently produced small, primitive, disorganized systems that bore no resemblance to the mature, massive galaxies lurking in the distant universe. The digital universe refused to build what the real universe already had. But as researchers refined their models and began to consider more extreme, alternative scenarios, a remarkable possibility emerged. What if the early universe experienced brief but incredibly intense periods of star formation? like cosmic bursts of creativity that compressed millions of years of evolution into geological instants. These starburst episodes could occur when young galaxies collided and merged, channeling vast amounts of cold gas directly into their centers. The resulting gravitational compression would trigger waves of star formation far more intense than anything seen in the modern universe. For these brief, brilliant periods, galaxies could convert nearly all of an entire gas cloud into new stars with unprecedented, almost perfect efficiency. The simulations showed that such intense episodes could create galaxies that were exceptionally bright, making them appear far more massive than they actually were. A galaxy undergoing an extreme starburst might appear to contain hundreds of billions of stars when its true stellar mass was much smaller. This discovery offered a potential bridge between observation and theory. The early universe might have been a more violent and dynamic place than we imagined, with frequent galaxy mergers and intense, short-lived starbursts creating the illusion of impossible maturity. It was a partial solution, a way to reconcile some of the data without rewriting the age of the universe. Computer models also revealed that cosmic dust played a crucial and previously underestimated role in making these early galaxies appear so red and ancient. In a starburst, young, hot stars produce enormous quantities of dust. This dust then absorbs the blue and ultraviolet light from those same stars and re-emits it in the infrared part of the spectrum. This process could make a relatively small, young galaxy appear both intensely red and deceptively massive when observed by Webb's sensitive infrared sensors. The simulation salvation suggested that the universe might not need to break its own rules to create the galaxies we observe. It might simply operate under more extreme, more violent, and more dusty conditions than we had previously imagined. The impossible galaxies might be a combination of genuine mass, brilliant starbursts, and cosmic dust clouds, a complex interplay of reality and illusion. Hidden in the static between radio stations, in the faint, pervasive hum of empty space, lies the afterglow of creation itself. The cosmic microwave background radiation, or CMB, fills every cubic inch of the universe with the faint warmth of the Big Bang. This ancient light, released when the universe was only 380,000 years old, provides our most direct and powerful evidence for the expanding universe model. The CMB appears almost perfectly uniform across the entire sky, with tiny, almost imperceptible temperature variations that match the predictions of Big Bang cosmology with extraordinary precision. These subtle fluctuations represent the seeds, the tiny density variations, that eventually grew under the influence of gravity into the galaxies and galaxy clusters we see today. They are like the ripples on a cosmic pond that have expanded over billions of years. But the tired light theory, the elegant alternative that could solve the impossible galaxy problem, faces a fundamental challenge in explaining this pervasive radiation. In an expanding universe, the CMB naturally cools as space stretches, perfectly maintaining the precise black body spectrum that we observe. It is a signature of a universe that was once hot and dense, and has been cooling ever since. In a static, tired light universe, this same radiation would need to be produced and maintained by some other, currently unknown mechanism. There would be no primordial fireball to explain its existence. Proponents of tired light have proposed various solutions to this problem, though none have gained widespread acceptance. Some suggest that the CMB represents the cumulative starlight from all the galaxies throughout history, redshifted by the tired light process until it appears as microwave radiation. Others propose that the radiation comes from complex interactions between photons and the cosmic medium itself, a kind of universal fog that generates a background glow. Recent studies have attempted to model how a tired light universe might produce the observed CMB. These models require a precise and careful fine-tuning of unknown physical processes. But they demonstrate that alternative explanations are not impossible, merely more complex and less natural than the explanation provided by the expanding universe model. The CMB also provides clues about the early universe's composition and evolution. Its nearly perfect uniformity suggests that the primordial cosmos was remarkably smooth, with only tiny variations in density that grew over time into the structures we see today. This smoothness, however, poses its own challenges for both expanding and static universe models. How did the early universe achieve such remarkable uniformity? Why do we see the same temperature in regions of the sky that, according to the standard model, should never have been in causal contact with each other? These questions, known as the horizon problem, hint at deeper mysteries about the nature of space and time themselves. As astronomers continue to map the CMB with ever greater precision, this ancient echo of creation remains a key witness in the ongoing trial of cosmological theories. In the current model of cosmology, dark matter makes up 85% of all the matter in the universe, providing the invisible gravitational scaffolding upon which galaxies and galaxy clusters form. This mysterious, unseen substance reveals itself only through its gravitational effects, bending the path of light and influencing the motion of visible matter. The massive early galaxies discovered by Webb pose a significant challenge to our current dark matter models. These galaxies appear to have formed within dark matter halos, vast, invisible gravitational wells that collect and hold the ordinary matter needed for star formation. But building such massive halos so early in cosmic history requires processes that push the very limits of our current dark matter theory. Computer simulations suggest that the largest dark matter halos in the early universe should have been relatively rare and small. Like galaxies, they would need billions of years to grow through the slow process of mergers and accretion into the massive structures capable of hosting these giant galaxies. The rapid appearance of these systems suggests either that dark matter behaves differently than we thought, or that our models are missing some crucial piece of physics. Some researchers have proposed that dark matter might have been more concentrated or clumpier in the early universe, allowing for the faster formation of these gravitational wells. Others suggest that dark matter could interact with itself in ways that accelerate structure formation beyond what our current predictions allow. These modifications would require fundamental changes to our understanding of this enigmatic and dominant substance. The tired light alternative offers a different perspective on the dark matter dilemma. If the universe is much older than we currently believe, then the dark matter halos would have had significantly more time to grow to massive sizes. The apparent youth of the distant galaxies would be an illusion caused by the tired light effect, while their true age would be billions of years greater. This scenario could potentially explain why these early galaxies appear so massive and well-formed. In a universe that is 26 billion years old instead of 14 billion, even the most distant galaxies would have had sufficient time to accumulate the vast dark matter structures needed for their formation. However, any alternative cosmology must still be able to explain all the other observational evidence for dark matter. From the rotation curves of spiral galaxies to the gravitational lensing effects seen in massive galaxy clusters, the dark matter dilemma perfectly illustrates how changing one aspect of our cosmological model can have far-reaching and complex consequences for our understanding of the universe's hidden components. As scientists continue their search for the elusive dark matter particles and study their gravitational effects on the cosmos, the early galaxy discoveries add a new and profound urgency to solving this cosmic mystery. The most distant galaxy merger ever observed tells a story of cosmic violence that directly challenges our understanding of how the early universe evolved. Located 13 billion light-years away, this ancient collision shows two already massive galaxies in the process of combining into something even larger and more complex. Galaxy mergers are among the most spectacular and formative events in the cosmos. Like cosmic car crashes that unfold in slow motion over hundreds of millions of years. When two galaxies collide, their mutual gravity distorts both systems, creating long, beautiful streams of stars called tidal tails that stretch across millions of light years. The central supermassive black holes at their hearts spiral inward, eventually combining in a final, cataclysmic burst of gravitational waves. But this particular merger poses a timing problem that echoes the broader crisis in cosmology. The two galaxies involved in this ancient dance are already massive and mature, containing billions of stars and well-developed structures. For such evolved systems to not only exist, but to find each other and collide when the universe was only 500 million years old seems almost impossible. It is like finding two ancient, crumbling castles that have crashed into each other in a land that was supposedly an empty field just yesterday. The merger also reveals surprising and crucial details about the nature of star formation in the early universe. The colliding galaxies show signs of intense stellar nurseries, regions where new stars are being born at rates far exceeding anything seen in the modern cosmos. This suggests that galaxy interactions might have been more common and far more violent in the primordial universe than we previously thought. Computer simulations of this distant merger suggest that the final, combined system would have a mass comparable to our own Milky Way galaxy. But our galaxy required over 13 billion years to reach its current size. Through countless smaller mergers and a long, steady history of star formation. How could the early universe produce a similar result in just a fraction of the time? The merger also provides clues about the role of supermassive black holes in the drama of galaxy evolution. Both of the colliding galaxies show signs of actively feeding black holes at their centers, suggesting that these cosmic monsters played a crucial role in regulating star formation and shaping the growth of galaxies from the very beginning of cosmic history. As astronomers study this ancient collision in unprecedented detail, it becomes clear that the early universe was a far more dynamic, chaotic, and violent place than we had previously imagined. The merger mayhem of the primordial cosmos might hold the key to understanding how these massive galaxies were able to form so quickly. This cosmic crash scene, preserved in light for 13 billion years, continues to challenge our assumptions about the quiet, peaceful evolution of the early universe. The ultimate test of any astronomical discovery lies in spectroscopy, a powerful technique that splits the light from a distant object into its component wavelengths, revealing the chemical composition, temperature, and motion of distant objects. When astronomers turned their most powerful spectroscopic instruments toward the impossible early galaxies, they hoped to find definitive evidence that would either confirm or refute the growing crisis in cosmology. The spectroscopic analysis painted a complex and fascinating picture. Some of the galaxies that appeared massive and ancient in the initial images turned out to be distant quasars, where the light from a supermassive black hole was so bright that it completely outshone its host galaxy. These cosmic lighthouses created the illusion of tremendous stellar mass, when the reality was dominated by the activity of the central black hole. But many other galaxies passed the spectroscopic test with flying colors. They showed the clear, unmistakable signatures of large stellar populations, complex chemical compositions, and the spectral features associated with mature, evolved galactic systems. These were not optical illusions or misidentified objects. They were genuine, massive galaxies existing in the early universe, a direct contradiction to the standard model. The chemical analysis of their light revealed particularly surprising results. These early galaxies contained significant amounts of heavy elements like carbon, oxygen, and iron, elements that should have been exceedingly rare in the primordial cosmos. The presence of these materials suggested that multiple generations of stars had already lived, died, and scattered their nuclear ash across space. This process of chemical enrichment normally takes billions of years to complete. In the modern universe, we can trace the gradual increase in the abundance of these heavy elements as successive generations of stars contribute to the cosmic recycling program. But these early galaxies seem to have compressed this entire, complex process into just a few 100 million years. The spectroscopic verdict also confirmed, beyond any doubt, that these galaxies were indeed at the enormous distances initially calculated. Their light had traveled for 13 billion years to reach Earth, meaning we were observing them as they existed when the universe was truly young. This ruled out the possibility that they were simply nearby objects masquerading as distant ones. Perhaps most significantly, the spectroscopic analysis revealed that these early galaxies were not just large, they were also incredibly diverse. Some showed signs of active, ongoing star formation, while others appeared to have already ceased making new stars, becoming quenched galaxies far earlier than any model had predicted. This diversity suggested a rich and complex ecosystem of galaxy types that challenged the simple, linear models of early cosmic evolution. The spectroscopic evidence left astronomers with an undeniable and deeply unsettling conclusion. The early universe had, somehow, produced massive, mature, and chemically enriched galaxies in record time. Long before the James Webb Telescope revealed its impossible galaxies, astronomers knew that the early universe underwent a dramatic and fundamental transformation called reionization. This process, occurring roughly 1 billion years after the Big Bang, saw the first stars and galaxies burn away the neutral hydrogen gas that filled all of space, creating the transparent, ionized cosmos we observe today. The massive early galaxies Webb discovered did not just witness this transformation, they were the primary engines driving it. Their intense star formation and the radiation from their supermassive black holes produced enough energetic photons to ionize vast volumes of space around them. These galaxies were not just breaking records for their size. They were literally reshaping the entire universe itself. Computer models of reionization had previously suggested that this process should have been a gradual one, with small, numerous galaxies slowly and patiently clearing the cosmic fog over hundreds of millions of years. But the presence of these massive, powerful early galaxies implies that reionization might have been far more violent and rapid than previously thought. Instead of a slow sunrise, it might have been more like a series of brilliant, overlapping flashes that cleared the darkness in a much shorter period. The implications of a more rapid reionization extend far beyond just the formation of galaxies. If reionization occurred faster than expected, it would affect the formation of the first stars, the growth of supermassive black holes, and the overall evolution of the large-scale cosmic structure. The entire timeline of early universe evolution might need to be compressed into a shorter, more dynamic period. Recent observations of the cosmic microwave background provide additional, independent evidence for a rapid reionization. The polarization patterns in this ancient radiation suggest that reionization began earlier and proceeded more quickly than the standard models had predicted. This independent confirmation supports the idea that the early universe was a more active and dynamic place than we had previously imagined. The reionization revolution also helps to explain why some of these early galaxies appear so red in Webb's images. The intense radiation from their stars and black holes would have heated the surrounding intergalactic medium, creating conditions that preferentially scatter blue light while allowing red light to pass through more easily. This effect could make young, star-forming galaxies appear redder and more mature than they actually are. As astronomers continue to study the epoch of reionization through both direct observation and computer simulation, the process emerges as a key link between the impossible early galaxies and the broader evolution of the cosmos. The reionization revolution transformed not just the universe's appearance, but our understanding of how quickly cosmic evolution can proceed under the most extreme conditions. As the evidence for these impossible early galaxies continued to mount, a small but growing group of scientists began to question whether the problem lay not with our understanding of galaxy formation, but with our most fundamental assumptions about the universe itself. Perhaps the Big Bang model, despite its many decades of success, was missing something crucial about the nature of space, time, and the grand arc of cosmic evolution. Alternative cosmologies had existed on the fringes of science for decades, but the Webb discoveries gave them a new relevance and a new urgency. These models proposed radically different explanations for the very observations that form the foundation of modern cosmology. From the cosmic microwave background to the apparent expansion of space itself. One class of these alternative models suggested that the universe might be cyclical rather than linear, with long periods of expansion followed by contraction in an eternal cosmic heartbeat. In such models, the current expansion phase might have been preceded by countless previous cycles, each one building up the complex structures that we observe today. This would provide a virtually unlimited amount of time for the formation and evolution of galaxies, easily explaining the mature appearance of the galaxies seen by Webb. Other models propose that our universe might be embedded in a higher dimensional space, a bulk with physical laws that differ from those we observe locally. These extra dimensions could provide additional sources of energy and matter that could accelerate the formation of galaxies beyond the limits imposed by our familiar four-dimensional physics. The steady-state cosmology, once a serious rival to the Big Bang model, also experienced a quiet renaissance. Modern versions of this theory attempted to explain the cosmic microwave background and other key observations while maintaining that the universe has always existed in roughly its current state. In such models, the apparent evolution of galaxies with distance might be explained by tired light or other, more exotic redshift mechanisms. Perhaps most intriguingly, some researchers propose that the universe might have experienced periods of modified physics, with fundamental constants and forces that differed from their current values. These variable constant models could potentially explain the rapid early formation of galaxies while maintaining a broad compatibility with other cosmological observations. Each of these alternative cosmologies faced significant challenges in explaining the full and complex range of astronomical observations that have been gathered over the past century. But the Webb discoveries demonstrated, with startling clarity, that even the standard model struggled to account for all of the available evidence. The crisis in cosmology had opened the door to possibilities that seemed impossible just a few years earlier. As scientists began to seriously explore these alternative frameworks, they found themselves grappling with fundamental questions about the nature of scientific truth and the ultimate limits of human knowledge about the cosmos. Hidden within the spectacular images of these early galaxies lies a subtler but equally important story. A story written in dust and gas, the raw materials from which all stars, planets, and life are born. The Webb telescope's powerful infrared vision revealed not just the galaxies themselves, but the complex chemistry and physics of their stellar nurseries. Dust grains, though microscopic in size, play an outsized role in the drama of galaxy evolution. These tiny particles, forged in the atmospheres of dying stars and in the fiery explosions of supernovae, absorb the harsh ultraviolet and visible starlight and re-emit it as gentle infrared radiation. This process warms the interstellar medium and profoundly affects how new generations of stars are able to form. In the early universe, dust should have been exceedingly rare, because it forms primarily from the heavy elements created in dying stars. But the massive early galaxies that Webb discovered contain surprisingly large and dense amounts of dust for their supposed age. This abundance of dust suggests that multiple generations of stars had already lived, died, and contributed their ashes to the cosmic recycling program. The presence of so much dust in such young galaxies implies that the entire cycle of stellar evolution proceeded far more rapidly than our current models predict. The gas dynamics within these galaxies also reveal crucial secrets about their formation. High-resolution spectroscopy shows that vast quantities of cold gas are flowing into the galactic centers at tremendous rates, feeding both the furious star formation and the growth of the central supermassive black holes. These inflow rates exceed anything observed in the modern universe, suggesting that these early galaxies operated under a completely different set of physical conditions. Computer simulations of gas dynamics in the early universe suggest that the higher density and temperature of the primordial cosmos might have enabled a more efficient process of gas cooling and subsequent star formation. The early universe's denser environment could have compressed gas clouds more effectively, triggering star formation at rates that are simply impossible in today's much more dilute cosmos. The dust and gas observations also provide clear clues about the role of galaxy mergers and interactions. Many of these early galaxies show disturbed and chaotic gas kinematics, suggesting that they are either currently in the process of merging or have recently experienced major gravitational interactions. This violent, dynamic environment could be the key to explaining their rapid assembly and their massive scale. As astronomers continue to study the dust and gas content of these early galaxies, they are uncovering a wealth of evidence for a universe that was far more chemically enriched and dynamically active than we had previously imagined. These microscopic particles and invisible gases hold the key to understanding how the cosmos evolved from a state of primordial simplicity to one of breathtaking complexity in record time. Nature provides astronomers with a powerful cosmic magnifying glass in the form of gravitational lensing, the bending of light by massive objects that can amplify and distort the appearance of the distant galaxies that lie behind them. Some of the most spectacular and distant early galaxy discoveries have been enhanced by this natural telescope effect. But the very phenomenon that allows us to see these faint objects also complicates our understanding of their true properties. When the light from a distant galaxy passes near a massive galaxy cluster on its journey to Earth, the cluster's immense gravity acts like a lens, bending and focusing the light rays. This effect can make faint, distant galaxies appear much brighter and larger than they actually are, bringing them into the view of our telescopes. For astronomers studying the early universe, gravitational lensing can reveal galaxies that would otherwise be completely invisible, pushing the boundaries of our observational capabilities. But lensing also creates a potential and significant source of confusion. A galaxy that appears incredibly massive and bright might actually be quite small, its light simply amplified by the intervening gravitational lens. Determining the true properties of these lensed galaxies requires a careful and complex modeling of the lensing effect and precise measurements of the light amplification. Some of the most impressive early galaxy discoveries have been gravitationally lensed, raising critical questions about whether their apparent masses are real or simply enhanced by this powerful lensing effect. Astronomers must carefully subtract the lensing amplification to determine the intrinsic, true properties of these distant systems. The lensing effect can also create multiple, distorted images of the same background galaxy, allowing astronomers to study different aspects of the same object from slightly different angles. These multiple images can reveal details about the galaxy's internal structure, its rate of star formation, and its chemical composition that would be impossible to observe in a single, unlensed image. Recent studies have used gravitational lensing to identify some of the most distant galaxies ever observed, pushing back the frontiers of the observable universe to just a few 100 million years after the Big Bang. These lensing-assisted discoveries reveal galaxies existing in an era when the universe was still in its infancy. The gravitational lens magnification effect demonstrates how the universe itself can serve as a powerful scientific instrument, using the natural warping of space-time to reveal otherwise invisible cosmic structures. As astronomers develop more sophisticated techniques for modeling and correcting these lensing effects, these natural telescopes will continue to provide crucial insights into the formation and evolution of the earliest galaxies. The complex interplay between gravitational lensing and the study of early galaxies highlights the delicate relationship between observation and interpretation in modern astronomy. Every galaxy tells the story of its formation through the combined light of its billions of stars, each one contributing its own unique spectral signature to the cosmic symphony. Astronomers use a technique called stellar population synthesis, the intricate process of modeling how different combinations of stars produce the total light we observe. To decode these complex galactic biographies, the process resembles a form of archaeological detective work, where scientists must reconstruct the distant past from the fragmentary, blended evidence of ancient light by analyzing the colors, brightness, and spectral features of a galaxy. Astronomers can determine how many stars it contains, what types of stars dominate its population, and how long ago its major episodes of star formation occurred. For the massive early galaxies discovered by Webb, the results of this stellar population synthesis reveal a puzzle wrapped in an enigma. These ancient systems show evidence of both young and old stellar populations coexisting, suggesting complex and rapid formation histories that challenge the simple, linear models of galaxy evolution. Some of these galaxies appear to have formed most of their stars in a few intense, short-lived bursts, while others show signs of a more gradual, steady assembly over time. The presence of a significant population of red giant stars in these early galaxies is particularly surprising and problematic. Red giants are evolved stars that have already exhausted the hydrogen fuel in their cores and have expanded to enormous sizes. The existence of these aged stars implies that the galaxies must have been forming stars for hundreds of millions of years before the epoch at which we observe them, further compressing the already impossible timeline. The chemical abundance patterns revealed by spectroscopy provide additional clues about the nature of stellar evolution in the early universe. The ratio of different heavy elements in a galaxy's stars records the history of nucleosynthesis, the process by which stars create these elements in their cores and scatter them into space when they die. These early galaxies show surprisingly high abundances of elements like oxygen and iron, suggesting a period of extremely rapid chemical evolution. The stellar population synthesis also reveals tantalizing evidence for what astronomers call a top-heavy initial mass function, a higher proportion of massive stars being born than is observed in the local universe. Massive stars live fast and die young, producing more heavy elements per unit of mass than their smaller, longer-lived counterparts. This effect could help to explain how these early galaxies were able to achieve such a rapid and dramatic chemical enrichment. Computer models of stellar population synthesis must also account for the different physical conditions that prevailed in the early universe, including higher gas densities, different radiation fields, and altered cooling processes. These environmental effects could have a significant impact on how stars form and evolve. As astronomers continue to refine their stellar population synthesis models, they are uncovering a wealth of evidence for a universe where both star formation and stellar evolution proceeded under conditions unlike anything we observe today. The overwhelming accumulation of evidence from the James Webb Space Telescope has reached a critical tipping point, where a series of individual anomalies have coalesced into a systematic and profound challenge to our entire understanding of the universe. What began as a few surprising discoveries about the size of early galaxies has now evolved into a fundamental question about the very nature of cosmic evolution itself. The paradigm shift extends far beyond the realm of astronomy and into the philosophy of science. The Webb discoveries demonstrate, with startling clarity, how quickly established and successful scientific theories can be challenged by new and unexpected observations, reminding us that our understanding of the universe is always provisional and subject to constant revision. The crisis in cosmology reflects the healthy and necessary skepticism that drives all scientific progress. Several competing explanations have now emerged to account for the existence of these impossible early galaxies. Some researchers favor a model of modified galaxy formation physics, proposing that star formation and black hole growth proceeded much faster and more efficiently in the early universe than our current models predict. Others advocate for more radical, alternative cosmologies that provide more time for galaxy assembly by fundamentally changing our understanding of space and time themselves. The debate has split the astronomical community into opposing camps, each defending their preferred interpretation of the growing body of evidence. Conference presentations and scientific papers now routinely address the early galaxy problem, with researchers proposing increasingly creative and sometimes audacious solutions to reconcile the new observations with established theory. The paradigm shift also reflects broader changes in the way that astronomy is conducted. The Webb telescope represents a qualitative, generational leap in our observational capability, allowing astronomers to study the early universe with a level of detail and precision that was previously unimaginable. This technological revolution has revealed phenomena that were completely invisible to previous generations of telescopes, opening up a new and unexpected window onto the primordial cosmos. As new data continues to pour in from Webb and other advanced instruments, this paradigm shift may accelerate even further. Each new observation has the potential to either strengthen the case for one of the alternative cosmologies or to reveal new and unexpected aspects of galaxy formation that could restore a sense of harmony between our observations and our theories. The paradigm shift in cosmology serves as a powerful reminder that science is not a static collection of fixed and unchanging truths, but a dynamic and ongoing process of discovery, debate, and revision. The impossible early galaxies have forced astronomers to confront the limits of their current knowledge and to seriously consider possibilities that seemed unthinkable just a few short years ago. History will ultimately judge whether this paradigm shift leads to a complete revolution in our understanding of the universe or simply a significant refinement of our existing theories. As we stand at the threshold of a new era in cosmology, the James Webb Space Telescope has given us a tantalizing glimpse of a universe that is far stranger and more complex than we ever imagined. The impossible early galaxies that sparked this crisis have forced us to confront fundamental questions about the nature of space, time, and the arc of cosmic evolution. The evidence points toward a universe where the rules of physics may have operated differently in the distant past, where galaxy formation proceeded at a breakneck speed, and where the entire timeline of cosmic evolution may need to be completely rewritten. Whether these discoveries ultimately support alternative cosmologies like the tired light model or led to significant modifications of the standard Big Bang model remains to be seen. What is clear is that the universe refuses to conform to our neat and tidy expectations. The massive early galaxies, the rapid formation of supermassive black holes, the accelerated pace of chemical evolution, all of these phenomena challenge our most basic assumptions about how the cosmos works. They remind us that despite centuries of scientific progress, we still have much to learn about the universe we inhabit. The Webb telescope has only just begun its mission of exploration. As it continues to peer deeper into space and further back in time, it will undoubtedly reveal additional surprises that will continue to challenge our understanding of cosmic evolution. Each new discovery has the potential to either deepen the current crisis in cosmology or to point the way toward revolutionary new insights about the nature of reality itself. The story of the impossible early galaxies is still being written. Future observations will ultimately determine whether these cosmic giants represent a fundamental flaw in our understanding of the universe, or simply the first glimpse of a more complex and fascinating cosmos than we ever dared to imagine. As we continue to explore the deepest mysteries of space and time, we are reminded that the universe is not only stranger than we imagine, it is stranger than we can imagine. The James Webb Space Telescope has opened a new and exciting chapter in humanity's long quest to understand our place in the cosmos. And the next revelations may be even more surprising than the discoveries that brought us here. The impossible has become possible, and the universe will never look the same again. The James Webb Space Telescope has revealed that the universe is not the orderly, predictable place we once believed it to be. From the moment astronomers first spotted those impossible red dots glowing in the cosmic dawn, we have been forced to confront the possibility that everything we thought we knew about the universe's birth might be wrong. These ancient galaxies, massive and mature when the cosmos was supposedly still in its infancy, have shattered our confidence in the Big Bang theory and opened the door to revolutionary new ideas about space, time, and the nature of reality itself. The evidence is undeniable. Galaxies that should not exist are scattered across the early universe like cosmic monuments to our ignorance. Whether they formed through some impossible new physics, exist in a universe far older than we had ever imagined, or represent the first tangible evidence for entirely new cosmological models. These discoveries have fundamentally changed our understanding of the cosmos. As we continue to explore the deepest mysteries of space and time, we stand at the threshold of a new scientific revolution. The impossible early galaxies may be just the beginning of a complete transformation in how we understand our place in the universe. The next discoveries await, and they promise to be even more extraordinary than the revelations that brought us here. What other cosmic secrets is the James Webb Space Telescope preparing to reveal? The journey of discovery has only just begun. The cosmos is calling, and we are finally ready to answer.